So I'm going to address, I actually am looking forward to the quantum gravity talks, but I'm going to address the question of what happens when you fall into a black hole. And the answer is, nobody really knows. Actually, there was, if you have a black hole, here's a black hole, and at least the exterior of it is black. And here's some poor Maxwell's demon-like person. I'll give him little horns. Her. Oh, no, sorry, I'm sorry. I said I called demons him. Falling into the hole. Then the classical version of what happens, if the hole is a very large hole, so large that there are not noticeable tidal effects due to gravitational curvature at the horizon, then the person falling into the hole won't actually feel anything particularly different from going through normal space-time. This is the classical picture of what happens when you fall into a black hole. He will see things differently because the starlight around him will be lensed. So he won't see, if he's looking into the hole, he won't see anything coming out from in front of him. But if he looks back, he'll see the entire night sky behind him because it's being lensed so it falls in the hole. So he will notice something different about things that are far away, but he will not notice anything at all different locally. Now, quantum mechanically, Hawking showed back in the 1970s that actually black holes are not completely black. I mean, a black hole is something that's so dense that light can't actually escape from it. There are actually first by the way, so and at a particular radius, if you get within a particular radius, then nothing can escape. By the way, do you know who it was who actually first calculated this Schwarzschild radius? 2gm over c squared? I'm sorry? Yeah, Laplace. I heard the right word back. I'm sorry, Laplace was the first one to calculate it, right? Because Mitchell suggested it, but he didn't calculate it, right? And so Mitchell pointed out that in Newtonian gravity, if you think of light as a particle and it has a finite velocity, and then there will be an escape velocity for an object that's particularly dense, and Laplace calculated that if an object starts out, a massive body has a radius smaller than this, and you start from the surface, you'll never get out. But in general relativistic black holes, the situation is worse. When you're in here, the light would go out and then it would fall back. In Newtonian gravity, here you just never even get out. Okay? Now, in the 1970s, Hawking showed that black holes are not entirely black, that there is actually some radiation that's emitted from the hole. But it did not look to Hawking, nor did it look to people who were calculating things in conventional quantum field theory on curved spacetime. One of the main practitioners here we have in Paul Davies and in Don Page, people who lived through those glory years. People didn't think that this Hawking radiation contained any information about what fell in, even though they didn't know for sure. And so they said, hey, when you fall into a black hole and things are quantum mechanical, stuff still doesn't get out. Okay. How might something escape from a hole? And in fact, so for years, Hawking and John Preskill had a debate that nothing got out. But recently, people are claiming stuff gets out of black holes. So why do they claim this, and how might this happen? So I'm now done with this, so maybe I could, actually, if I could just ask you, Anthony, to take it and put it down. In the string theory community, there is a strong conviction based on string theory that the time evolution of anything, including gravitational stuff, is unitary. And so if stuff falls into a black hole and the black hole evaporates, then the stuff should get out. Okay. Now, this is held very dearly by many people in the string theory community. It's due to the ADS-CFT correspondence. But if not being a member of that community, I have some skepticism about it. I think, since we don't know what goes on in a black hole, the question is still open. But let me actually tell you now, the next pictures I'm going to draw are going to tell you how you might be able to escape from a black hole using something called the Horwitz-Maldacena mechanism. And I'm going to draw pictures, but actually the pictures have mathematical significance, and I'm going to give you this mathematical significance over here. So when I draw something like this, then this is actually just going to be equal to...
You broke the rule.
Oh, I broke the rule. Quick, before it dries. Where's the whiteboard eraser? There. Oh my God, yeah, I'm a jerk. It says W. Great. Yeah. Okay. Who could have thought that doing something scientific would actually ever cause anybody to get upset? Okay. Let's try it again. Let's see if this now works. Yeah, when I draw something like this, then this means that I'm creating, this is equal to a singlet state. So in quantum information terms, it looks like that. And when I draw something like this, I'm sorry? Okay. Let me use one of these pens. I'll draw it over here. Yeah, I think it's just because it's dark over there. Yeah, maybe we can move that with we can move that with the light. Is that what might work? So let me start drawing pictures while they move this around. See, this is one of the. I'm not using PowerPoint, but luckily I have many people to help me. So can you see it now? Yeah. So and this is, I'll call this is just a singlet state, and this is the ket version of it, and this is just the bra version of it. So this right here, when I put them together, this means contraction of these two things, and this is just a number. So this is just equal to psi, which in this case is equal to 1. All right? So this is what I'm going to do now. When I draw stuff like this, this will be the notation I'm using. So then if you draw the picture of what happens when something falls into a black hole, here is the normal picture. Here is the singularity, the part in the middle of the black hole where everything gets mushed to nothingness. Here is the horizon. So this is the singularity. This is the horizon, the point of no return. When you fall into the black hole, something falling into the black hole will go in here and be mushed to nothingness at the singularity. That's the conventional classical picture, and also the picture in quantum field theory on curved space-time. The Hawking radiation consists of singlets. I'm going to draw them with little arrows too. The arrows tell you where the minus sign is here. Consists of singlets at the horizon, particle-antiparticle pairs, where a positive energy antiparticle, the positive energy part of the pair escapes to infinity. The negative energy part falls into the black hole and is also smushed at the horizon. Okay? So Horwitz and Maldacena proposed the following dastardly proposal. They said, well, what does happen at the horizon? Well, the answer is, of course, nobody knows. Now, to an experimentalist, the horizon, sorry, what happens at the singularity? Excuse me. To an experimentalist, this is bad, but to a theorist, the fact that nobody knows is an opportunity, because you can say, we'll make it whatever we want it to be, all right? So they said, well, since nobody knows, we're free to postulate anything we like. And so they said, OK, what happens here is that the infalling stuff, let's call this quantum state chi, gets smushed to nothingness as a singlet with the infalling half of the infalling Hawking radiation. That's what they postulated. And why do they postulate that? Because then actually, I won't go through the physics of teleportation, of quantum teleportation, but the physics of quantum teleportation just tells you it's easy to calculate that this thing is then that same state, chi. Because these things these funny-looking things over here basically have the feature that you can show that sorry, where's that eraser? It's a simple exercise in looking at drawing these things like this to show that something that looks like this can be pulled tight, and this is actually just equal to that. Okay? It's kind of cool. Now, I should note that though this sounds innocuous and it looks like it solves all your problems, this is completely illegal in ordinary quantum mechanics, because being projected onto a singlet is not a unitary process. It's not even a linear process. So this violates linearity and unitarity of quantum mechanics. Nonetheless, it certainly allows stuff to escape from the black hole. And in fact, well, so are there questions about this point? This is the Horwitz-Maldacena mechanism in a nutshell. Okay, then I will go on. All right, so very well, this is good. Stuff could escape from a black hole if you're willing to allow something horrible and non-unitary to happen. But you might note here that actually it's not as bad as you might think, because in fact, if the stuff that's falling into the hole never interacts with, if this is a unitary transformation on the stuff falling into the hole, this is a unitary transformation on the infalling Hawking radiation. And if the stuff falling into the hole never interacts with the infalling Hawking radiation, which, by the way, is what normally is supposed to happen to inertial things falling into a black hole, then what comes out is just equal to uv transpose times chi. And so what happens is actually just a unitary transformation of the stuff that comes out. So a black hole, even though you're violating unitarity here, a black hole could still evaporate in a unitary fashion. So when all is said and done, everything is unitary. Okay? So I'm now done with this one right here.
About 10 more minutes.
Good. So what's not to like about this, apart from the hideous violations of unitarity? Well, violations of unitarity lead to weird stuff happening, okay? So the first thing to notice is that if this thing right here is this state chi, and this thing right here is the state chi, then because if I look at the surfaces of constant time for a distant observer out here, then these things exist on the same surface of constant time, which means I now have a clone of the infalling state. So this non-unitarity here, in fact non-linearity, is violating the quantum no-cloning theorem, which you shouldn't be maybe too surprised about because, hey, the quantum no-cloning theorem is proved by assuming unitarity, and it's not unitary. Okay. But you know what? You know, if you want to make an omelet, you have got to break eggs, right? And if you want to escape from a black hole, you basically have to go faster than the speed of light, so something's got to give. And actually, the lack of superluminal travel in quantum mechanics, and lack of superluminal travel in relativity and unitarity in quantum mechanics are related to each other. However, even worse, let me draw this here, is if this is now a singlet state right here. So this thing that's going in here is entangled with this right here. And this right here is, of course, then entangled with this right here. But hold it, this was half of a singlet pair where this is the Hawking radiation. So this is simultaneously entangled to here and entangled to there, which violates something called monogamy of entanglement, which is an important feature of quantum states, now not of unitary evolutions. However, that's also okay because, in fact, if you go and you look at quantum theories which have this final state projection in it, like the Aharonov-Vaidman weak value theory, then you have to give up the notion of a quantum state. There's no well-defined quantum state at a particular time, which is maybe not surprising because in this picture you have to propagate this state forward in time, but then you have to propagate this state backwards in time, and they meet. And they can't agree on which state is which. So there's no unambiguous notion of a quantum state. So again, everything is okay. You know, this shows you, once you commit one crime, what do they say? Well, once you've lost your reputation, you can only use your reputation once. So, you know. And since I already lost mine yesterday. All right. So everything actually looks kind of okay. You could get a unitary evaporation of a black hole, and when all this goes away, this is the point where the black hole goes away. Up here, everything could have been unitary. But it's still not okay enough because when this Horwitz-Maldacena model came out, John Preskill and let's see, was it Daniel Gottesman, I think? They wrote an article pointing out that if the infalling Hawking radiation can interact with the stuff that's falling into the hole, and there's no real reason why it shouldn't, then this is not unitary. So this does not equal U chi. In fact, it could be as far from unitary as you desire. So, and since this is a generic looking kind of situation, then this seemed to be kind of bad. And I talked with Horwitz a few years after the proposal. This was, by the way, Horwitz-Maldacena was now getting on 10 years ago, I think. And they seemed to not to, right, thank you. And they seemed to think, well, I don't know, maybe not, okay. But then afterwards, so I got interested in this, and I pointed out that if this is random, so if U is random, sufficiently random, and of course the devil is in the sufficiently, or if it's completely random, then this actually is equal to U chi plus a tiny correction, which goes as e to the minus the mass of the whole squared. The point is that for this to work, it really comes from teleportation. For this to be unitary, this right here has to be a perfectly entangled state. If it's not perfectly entangled, for instance, if it's a product state, then no information comes out at all. However, if you take any state and you apply a random transformation to it, or more strictly what's called a 2 design, but let's leave that aside. If you apply a random transformation, then this state will be almost perfectly random, as Don Page knows, because back in the 80s, he and I worked on this question of, how entangled is a random state? And the answer is, from the Page rule, almost perfectly entangled. In fact, no matter how big the state, it should be within 1 bit of perfectly entangled. Okay, so in fact, you could actually get almost unitarity with a tiny weensy correction to this. And in fact, if you put even a little tiny bit of quantum error correction on your states going in, and there intrinsically is such an error correction because the Hilbert space of the states going in is much smaller than the Hilbert space of the states going out, which gives you automatic redundancy, then you should be able to reproduce this state going into a very, very high degree of accuracy. Okay, so I'm almost done here, and I believe I only have like 1 or 2 minutes. Is that right? 2. Okay, good. Now, all kinds of interesting problems remain here. I mean, first of all, if you believe in exact unitarity, then you're not satisfied with even having an amount. This kind of unitarity, if m is larger than 5, any self-respecting quantum computer designer would say, awesome, we'll take it, right? But if you believe in exact unitary, it's not so good. Remains the question about what does it feel like to fall into a black hole? Well, according to this picture right here, it's really very close to the ordinary picture. It just feels you cross the horizon, everything's fine. You get kind of scrambled up near the singularity, which you expect because tidal forces are ripping you apart. And then, it's like, whoa, what's that horrible singularity coming up? Something happens, you don't remember it, and then, whew, what was that? What happened? You find yourself outside the hole. Now, actually, there remains a problem. I'm sorry, did somebody have a comment?
That's only if someone reconstructs you from the Hawking region.
Yeah, exactly. This is U prime, right? U prime. U prime, if U is random, then by God, U prime sure is too. Right, so there remain very interesting questions. So how do you assign the probabilities to events here? And Raphael Busso and his colleague Stanford have just written a very nice paper about under what circumstances you can construct decoherent histories for events going in and out of the hole. And they find more interesting things. Actually, just to give away, since Raphael's not going to be talking about this, I'm allowed to give away the point of your paper. So if this U is completely random, then actually things are fine. Because of a fact, actually, I have a paper from this a long time ago about quantum chaos and decoherent histories, that if U is random, then histories going through here are almost completely decoherent. If it's not, then you certainly have features that something that happens in here, like the decision to make a measurement in here or not, can affect what happens outside the hole. Let me just finish off because we're almost done. So I guess from Scott's point, even if this model is true, you should be a little leery about falling into a black hole. And if you do fall into a black hole, I can only quote this nice paper which says you might be tempted if you fall into a black hole to fire your rocket to say, oh my God, it looks like I passed the horizon. Let's just like dump all the fuel, go put all the fuel we can to going back in the other direction. But it turns out that if you do that, you still end up hitting the singularity, and because you're accelerating, your clock is ticking slower, so in your own clock you hit the singularity sooner. So I guess my final words of advice to you are, if you fall into a black hole, don't struggle.